In this video, we're going to take a look at Born Haber cycles, so what they are and how we can do calculations with them. So a Born Haber cycle is essentially an enthalpy level diagram that's going to break down the formation of an ionic compound into a series of simpler steps. Essentially, this is an application of Hess's law. And the reason why we create these or use these is because we can calculate quantities that are difficult to measure directly, specifically lattice enthalpies. They are not an easy thing to measure directly, and so we can get values of lattice enthalpies using a Born Haber cycle from values that are measured much more easily. So on the video slide here, we've got a generalized version of what a Born Haber cycle is. So let's go through this step by step. So let's start down here with our delta HF formation. So this is the part where this is the formation of an ionic compound. Okay, so when we form an ionic compound, we're taking some metal and we're taking some nonmetal and creating our ionic compound. In this case, it's an MX. Now, we can break this down and go in indirect route to get that value. So if we're going our indirect route, I'm just going to draw the arrow going around this way. So starting off with down here, we're going to start following our indirect route with our atomization enthalpy of our metal. So that's taking our solid metal and changing it into the gaseous state. From there, we need to ionize our metal. So we're going to take the ionization energy of our metal to create our M+. From here, our next sort of step up is the atomization of our X. So we're taking this X in or X2 in our gaseous state, and we're creating just the atom by itself in its gaseous state. From there, we need to undergo electron affinities. We need to add an electron to our nonmetal to create an X minus. And then from here, our M plus and our X minus is our lattice enthalpy to MX. Now, everything here, if we take a look here, here, and here, is all going with the direction of our indirect route. But remember, lattice enthalpy is endothermic, so we're going to have to flip the sign of this one in our calculations in order to get down to our enthalpy of formation. So if we were, for example, trying to find our enthalpy of formation of this particular reaction, we would be taking our enthalpy of atomization of our metal. We'd be taking our ionization energy of our metal, our atomization enthalpy of our nonmetal, and then our electron affinity of our nonmetal. And then finally, we'd be subtracting our enthalpy, our lattice enthalpy, okay, because it's endothermic and it's going against the direction of our indirect route. So this is essentially the equation that we're going to be using in most of our calculations. So let's take a look at an example. So we want to determine the lattice enthalpy of potassium bromide using the provided Born Haber cycle. So I think first, kind of what you need to do is orient yourself and ask yourself, what are we looking for? We're looking for lattice enthalpy. So let's circle that here, and that is what we need. So in order to get there, maybe let's draw in our indirect route in a different color. We're going to start at the one end of the arrow, and we're going to follow it around to create our indirect route. And I think it's really good to go through and do this because it's going to help you know which signs to use for your different values. So your arrow of your indirect route should always end with your arrow of what you're looking for, and the beginning of your indirect route should always start at the beginning of the arrow of what you're looking for. Hopefully that makes sense. So let's follow our indirect route around and set up our equations. We're trying to find our lattice enthalpy. And starting off first, we're starting with the delta H of formation. Now this arrow goes against our indirect route, so we want to take the negative of that. And then we're going to take next our delta H of atomization of potassium. That's with our arrows, so that's good. We can keep the value as is. Same with the ionization energy. Same with the atomization enthalpy of bromine. And same with the electron affinity of bromine. So the only one we needed to switch was our enthalpy of formation. So let's go through now and put in all our values. So instead of negative 392, I guess we could go negative 392. And then we're going to add 89, 419, 112, and negative 325. So if we do this calculation, we should get 687 kilojoules per mole. You know you've done this right. At least one way to check is that we know the direction that the arrow's drawn here for our lattice enthalpy means that it should be endothermic. So you can double check, make sure it's endothermic. If it is, you're probably good. Now let's take a look at one more example. Sometimes you might be asked for something that's a little bit more complicated, like magnesium oxide. So here we want to find the enthalpy of formation. So let's find that first on our Born Haber cycle. That's right here. Now, because it's magnesium oxide, we actually have to create 2 plus and 2 minus ions. So we have to go through the ionization energy twice and the electron affinity twice. We have the first one and then we have the second one for both. So that's why this Born Haber cycle looks a bit bigger, but it's no different. So let's start our indirect route where our arrow of our thing is that we want to find. So I'm just going to draw it up around here and then bring it back down over here, ending where the arrow starts of, or the arrow ends for our delta H of formation. Okay, now if we follow this around, we are finding our delta H of formation. We're going to take the delta H of atomization of our magnesium. Then we're going to take the ionization energy 1. We're going to take ionization energy 2. All of these arrows are with our indirect routes, so we're good so far. We're going to take the delta H of atomization of our oxygen, then our 2 electron affinities. Okay, and everything's with the direction of our indirect route, so this is good. The only one we're going to need to flip is our lattice enthalpy. Okay, and so we're just going to subtract that from here. So let's put in our values. We got 148, we got 738, we got 1451, 249, then we're going to add negative 141, we're going to add 753, and then we're going to subtract 3791. Okay. And if we do the math for this, we get negative 593 kilojoules per mole. So a few extra things that we've had to add into our calculation, but the steps are exactly the same. So that is a Born Haber cycle. That is how we do various calculations with Born Haber cycles. So that's it for this video. We'll see you in the next one.